Have you ever wondered why the night sky feels close, even when it's unimaginably far away? Right now, the moon looks nearby. The stars seem pinned to a flat, silent sky. But what you're really seeing is your mind folding billions of kilometers into something familiar, something safe. Distance is the first truth we lose when we look up, and once it's gone, the universe stops making sense. Tonight, you won't just learn how far everything is, you'll begin to feel it. And once you understand the true scale of cosmic distance, the sky above you will never look the same again. Before we begin, if you feel connected to this space, a quick like or subscribe would truly mean a lot. It's a small gesture, but it really helps the channel grow. Thank you for being here. Now, together, let's drift into space. Look up. It feels like the universe is right there, like you could almost touch it. A black dome, a sprinkling of lights, a flat, silent roof above our heads. But this is the first cosmic lie we ever learn, because the sky is not a ceiling, it is not even a surface. It is an ocean of depth so extreme that our minds quietly collapse under it. And that collapse happens for a simple reason. Our eyes were never built for the true scale of distance. We were built for rooms, for trees, for cliffs, for the short, urgent geometry of survival. So when we stare into space, our ancient instincts do what they always do. They shrink it, they flatten it, they make it feel near. But then comes the disturbing part. Even the most familiar objects in the sky are already far enough to break our intuition, and once intuition breaks, it never fully recovers. We need to admit something uncomfortable. When we look up, we are not seeing distance, we are seeing angles. We are seeing a two-dimensional image painted onto the inside of our vision, and our brain is forced to guess the depth. On Earth, that guessing usually works, because Earth gives us clues, shadows, texture, perspective, motion, and a powerful trick called depth perception, the small difference between what our left eye sees and what our right eye sees. That difference is enough to tell us what's near and what's far, but it only works within a limited range. As distance grows, that left-right difference becomes microscopic, and beyond a certain point, the world stops feeling three-dimensional. It turns into a postcard. That's why a far mountain can look close enough to reach in an hour, and still take the entire day. That's why a jet can look like it's crawling across the sky, while moving faster than sound. Our senses don't measure space the way physics does. They measure what space feels like, and the sky is where that feeling becomes unreliable, because the sky removes the clues our brain depends on. No walls, no reference objects, no texture, no familiar size, just darkness and points of light. So the brain does what it always does when it lacks information. It simplifies. It assumes the stars are placed on a surface, a dome, a shell, a beautiful illusion, designed by biology. But this is where everything changes, because the universe doesn't just disagree with our intuition, it violates it. There's a brutal concept hiding inside almost everything we see in the sky. Angular size, not how big something is, but how big it appears. We can prove this with our own bodies. Hold your thumb out at arm's length. It covers a surprisingly large portion of the world. Move that thumb closer to your eye, and it swallows everything. Move it farther away, and it shrinks. The thumb doesn't change, only the angle it takes up in your vision. That's angular size, and it's the core trap our brain falls into, because our brain uses apparent size to guess distance, but that only works when we already know the object's real size. If we don't know the real size, our brain can't solve the equation, so it invents an answer. And in the night sky, almost nothing has a familiar, reliable size. A star could be enormous or small, a planet could be near or far, a galaxy could be a colossal structure or a tiny smudge. The sky gives us brightness and position, but not scale. So our brain does what it does under uncertainty. It compresses the universe into something manageable. A map, a flat display, a dome of lights. Except it's wrong. And the most famous example of this failure is sitting above us every single day. Here's the strange part. The moon and the sun look almost the same size in the sky. That's not poetry, that's geometry. Both appear about half a degree across, roughly the width of your fingertip held at arm's length. And that visual coincidence is so perfect, it allows total solar eclipses to happen. The moon can cover the sun almost exactly, and we instinctively read that as proximity. We feel deep down that if two objects look the same size, they must be the same size, or they must be at similar distances. But neither is true. The sun is vastly larger than the moon, about 400 times wider, and it is also about 400 times farther away. So by pure coincidence of ratios, the angles match. Not because they are close, not because the universe is neat, but because we got astronomically lucky. And that luck becomes a psychological trap, because our eyes don't see 400 times, our eyes see same size, so our brain quietly files them into the same mental folder. Nearby things in the sky, but the reality is monstrous. The moon is already far enough to break the way we naturally think about distance. We like to believe we understand distance. We live inside it. We drive through it. We walk across it. But our intuition is not built for large scales. Most of our everyday depth judgments are strongest at short range, across a room, across a street, across a field. Once we push beyond a few kilometers, a few miles, our brains start relying on guesses and learned labels, not direct perception. We start saying things like, "It's just over there. Looks close. We can make it before sunset." And then distance reveals its true nature. It doesn't feel like anything. It is an invisible barrier. And the sky is the most extreme version of that barrier because it removes the feedback loop. On Earth, you can walk toward a mountain and watch it grow. In space, you can stare at the moon for hours, and it never feels closer. It never approaches. It stays the same size, the same brightness, the same calm illusion. So we assume we understand it. But then we learn the number. The average distance from Earth to the moon is about 384,400 kilometers, about 238,900 miles. Say that slowly. 384,000 kilometers, 238,000 miles. That number is not just far, it's far in a way we cannot naturally imagine. And scientists don't ask us to feel it as a number. They ask us to feel it as time, a signal traveling at the speed of light. The fastest thing in the universe takes about 1.3 seconds to go one way. So if we spoke to someone standing on the moon, there would be a pause. Not because of technology, not because of delay in equipment, but because distance itself imposes silence, and suddenly the moon stops being a nearby object. It becomes a separation, a gap, a truth. NASA engineers, mission planners, and the Apollo astronauts lived inside that gap, and the psychological weight of it is easy to miss, because the moon still looks like a coin in the sky. The illusion holds, even when reality is screaming. And this creates a new problem. If the moon is already that far, then what about everything else we see? Imagine this. We're standing in a dark room. The ceiling is painted black. Someone has placed tiny lights everywhere. Some are taped to the ceiling, but others are floating in the air on invisible strings at wildly different depths. Now turn off the normal lights. All we can see are points of glow. From where we stand, many of those lights look like they're on the ceiling. Some look close, some look far, but without reference, we cannot tell. We're not seeing depth. We're seeing a pattern. That's us, every night. The universe is the room, the stars are the lights, and the darkness steals our depth cues. So we do what humans always do. We mistake the pattern for a surface. But the universe isn't a surface. It's a volume, a terrifying one. And if you've ever felt, even for a second, that the sky is up there, like a roof, that's not ignorance, that's biology. Your brain is trying to protect you from the truth, because the truth is too large to hold in one thought. The truth is that distance isn't just a measurement, it's an experience we were never designed to process. And once we accept that, we begin to understand why the universe feels so quiet, so unreachable, so impossibly empty. But we're not ready for that yet. First, we need to confront the first invisible wall: distance. This is the uncomfortable reveal. Before we ever talk about stars, before we talk about galaxies, before we talk about the edge of the observable universe, we have to face the first failure point: our senses, our intuition, our internal ruler that tells us what is near and what is far. Because the universe doesn't just extend beyond our neighborhoods, it extends beyond our evolutionary limits. And the sky looks flat and close for the same reason a photograph looks flat and close. We are seeing a projection, a slice, an image, not the structure. And angular size is the mechanism of the illusion. It makes gigantic things appear small. It makes distant things appear manageable. It makes the cosmos feel like a decoration instead of a reality. The moon and sun sharing the same apparent size is the cleanest example. A coincidence so precise it shaped human myth, calendars, and wonder. And yet the coincidence hides a harsher truth. We cannot trust how space feels. We can only trust what we measure. That's why astronomy is not just about looking. It's about learning how to correct what looking does to us. Einstein understood this in a deeper way. Not just that space is vast, but that our common sense is not a reliable guide to the universe. And once we accept that, we unlock the next step. Because if the sky can fool us this easily, then we need a baseline, a ruler we can actually live inside, a distance our bodies can understand. And this is where the real question begins. If the moon is already far enough to shatter our intuition, then what is the largest distance we have truly lived? Not imagined, not calculated on paper, lived. The answer is not in the stars, it's beneath our feet. And once we set that baseline, everything that comes after becomes even more disturbing. Because the moment we measure Earth itself, we realize we've been living inside a scale we barely understand, and that is where the true journey begins. Before we dare to measure the stars, before we talk about the moon or the planets or the long silent corridors between suns, we have to face a quieter truth. The largest distance most of us will ever physically live inside is not cosmic. It's Earth, not Earth as a picture, not Earth as a globe on a desk, Earth as a scale, a massive curved distance that wraps under our feet and keeps going, even when our eyes insist it should stop. Because the strangest thing about cosmic distance is this: we try to understand the universe using a ruler we've barely ever held. Our instincts say Earth is big, but our minds do not actually feel how big. And that's where the story cracks open. Because if we can't truly sense our own planet's scale, then everything beyond it is going to become disturbing. Let's give ourselves a baseline we can trust. Earth's diameter is about 12,742 kilometers, about 7,918 miles. Say it slowly: 12,742 kilometers, 7,918 miles. That's not a number we naturally carry in our bodies. We don't live in diameters. We live in streets and rooms and neighborhoods, so our brains shrink the planet into something manageable. A world, a place, a background. But NASA engineers, ESA mission teams, and generations of navigators didn't treat Earth like a background. They treated it like a measurement problem, a shape you could test, a curve you could verify, a distance you could suffer through, one step at a time. And long before rockets, long before satellites, humans began to suspect the truth. Eratosthenes in ancient Greece used shadows and geometry to estimate Earth's circumference more than 2,000 years ago. No spacecraft, no computers, just sunlight, observation, and the willingness to believe Earth was bigger than it felt. That willingness is where cosmic understanding begins. But then comes the modern shock. Even with planes and satellites and maps, Earth still strains our intuition, because Earth is the first place where distance stops behaving like a human experience and starts behaving like physics. Here is the problem. We don't see curvature easily. At the scale of a human body, Earth looks flat. We can walk forward for hours and feel no bend beneath us. Our senses were built for local truth. They were not built for planet-sized truth. And this is why the horizon is such a powerful illusion. It feels like an edge. It feels like the world ends there. But the horizon isn't an edge. It's our vision, failing. It's the planet curving away so gently that our eyes can't hold it. And if we can't see Earth's curve while standing on Earth, then our brains do what they always do under uncertainty. They simplify. They pretend the world is smaller, flatter, nearer. But the moment we try to cross serious distances, the lie collapses. Consider a single line around the planet. Earth's equatorial circumference is about 40,075 kilometers, about 24,901 miles. That's one loop, one ring of distance around our home. Now map that onto human life. A long road trip across a large country can feel exhausting, but Earth is not a road trip. Earth is a loop so long that it can swallow months, even years, depending on how we travel. And that's why circumnavigation became one of humanity's first brutal lessons in scale. When Magellan's expedition began, the first circumnavigation in 1519, and the survivors returned in 1522, it wasn't just a geographic achievement, it was a psychological one. It proved the world wasn't a patch of land surrounded by mystery. It was a sphere, a closed distance, a planet-scale truth. But this was only the beginning, because once we wrapped ships around Earth, that we did something even stranger. We left the surface entirely. There's a quiet violence in the idea of orbit. Orbit means you are moving so fast that as you fall, the planet curves away beneath you. You never hit the ground. You fall forever. And Earth keeps missing you. This isn't poetic, it's physics, and it took us a long time to do it. Then, in 1957, the Soviet Union launched Sputnik, the first artificial satellite. A small object became a moving proof that Earth was not just a place. It was a gravitational system, a ruler, a baseline. And soon after, NASA, the Soviet space program, and later ESA and others began building a new way to measure distance, not by roads, not by oceans, but by altitude and velocity. Look at the International Space Station. Its altitude is roughly 400 kilometers, about 250 miles above Earth. That sounds close. It sounds like a short hop compared to the vastness of space. But that closeness is part of the trap, because the ISS is not hanging above us like a ceiling lamp. It's moving at about 28,000 kilometers per hour, about 17,500 miles per hour. Fast enough to cross a large city in seconds. Fast enough to cross a country in minutes. It completes an orbit in roughly 90 minutes. And suddenly we realize something uncomfortable. Space doesn't begin where things feel far. It begins where Earth's scale becomes undeniable, where our normal sense of motion becomes irrelevant, where distance is no longer walked. It is flown at speeds that crush intuition. But then comes the deeper boundary, not the ISS, not the edge of the atmosphere in a poetic sense, a specific line we use to mark the transition from Earth's domain to space. The internationally recognized boundary often used is the Kármán line at 100 kilometers, about 62 miles above sea level. It is not a wall, it's not a gate, it's a convention, a human attempt to draw a clean border on something nature does not separate neatly. Above this altitude, the air becomes so thin that aerodynamic flight becomes impractical. To stay up, you can't rely on wings the way airplanes do. You begin relying on orbital mechanics, on momentum, on falling around Earth. This is where the story cracks open again. Because if we scale Earth down to something we can hold, the Kármán line becomes almost nothing. Here's the simple mapping. Picture this. Imagine a globe that is 1 meter wide, about 3 feet across, sitting in front of us. On that globe, Earth's full diameter becomes that 1 meter. Now ask, where is the Kármán line? On this globe, the edge of space would be only about 8 millimeters above the surface, less than the thickness of a finger, a thin band, a slight rise, so thin it feels absurd, and yet crossing that thin band required the most complex machines our species has ever built. Because the distance isn't just vertical, the distance is conceptual. It's the transition from living on a surface to living inside motion. And once we accept that, Earth stops being the ground. Earth becomes a baseline for everything. But we're not done. Because even at 100 kilometers, 62 miles, our minds still think we're basically here. And that is where the universe sets another trap. We often imagine Earth as a familiar thing. But familiarity is not understanding. Earth is so large that even now, most of us have never experienced its full scale. We experience fragments, a region, a coast, a flight path, a map. But maps lie in their own way. They flatten, they distort, they turn curvature into convenience. And this is why a long-distance flight can feel like a small story, just hours, a meal, a landing. But the distance underneath that story is enormous. If we fly a long route, say 10,000 kilometers, about 6,200 miles, we can cross entire hemispheres. And our bodies barely register what just happened. We sit still, while Earth's scale moves beneath us. Our senses never evolved for that. So even Earth, just Earth, becomes too large to feel. And if Earth is too large to feel, then every nearby object in the sky is going to be misunderstood. This is why astronauts, mission controllers, and physicists talk about Earth with a kind of quiet respect. Not because it's mystical, but because it is the first real scale that forces discipline. Numbers, units, precision, and translation into human terms. Because the cosmos doesn't care what feels close, only what is. And if you've ever stood outside at night, looking up, feeling like space begins just beyond the clouds, you're not wrong for feeling that. But you are standing on a planet so large that you can't truly sense its curvature with your body. You are living on a sphere with a diameter of 12,742 kilometers, 7,918 miles, and your brain still wants to treat it like a flat floor. That's how powerful the illusion is. Earth is the first test, and most of us don't even realize we're failing it. So this is what we do now. We stop trying to understand the universe with instinct. We build a ruler, and Earth becomes the first unit we trust. Earth is our baseline, a diameter of 12,742 kilometers, 7,918 miles, a circumference of 40,075 kilometers, 24,901 miles, a boundary to space we often place at 100 kilometers, 62 miles, a realm where orbit demands speeds around 28,000 kilometers per hour, 17,500 miles per hour. These aren't just facts, they are the first hard edges of reality, because once we accept Earth's scale, we can finally see what comes next. And what comes next is not a little farther, it is a different category of far, because the moment we leave Earth's baseline, we meet the first object that still looks close, but already breaks the human mind. So here's the question hanging in the dark. If Earth is the largest distance we've truly lived inside, what happens when we step beyond Earth's ruler? What happens when the next destination is not a continent, not an ocean, not an orbit, but the moon? It hangs there like it's within reach, a calm, bright coin. But the number behind it is the first real fracture in our intuition, and once we cross that distance, everything we thought we understood about near collapses. The moon looks close, a clean, pale coin pinned to the night. It feels like the next step, like the first doorway into real space. But that feeling is the most dangerous part, because the moon is not nearby. The moon is the first distance that shatters our instincts, while still pretending to be gentle. It's close enough to look familiar, yet far enough to make communication slow, isolation absolute, and rescue almost meaningless. And once we truly absorb that distance, we stop using words like nearby so casually, because if the closest world is already this far, then the rest of the universe is about to become unimaginably silent. Let's put the first hard number on the table. The average distance from Earth to the Moon is about 384,400 kilometers, about 238,900 miles. Say it slowly, 384,000 kilometers, 238,000 miles. Our brains don't know what to do with that, so we translate it into something we can feel. Earth's diameter is about 12,742 kilometers, about 7,918 miles. That means the Moon is roughly 30 Earth diameters away, 30 Earths laid end to end just to bridge the gap. And here's the strange part. Even after we say the number, even after we repeat it, the Moon still looks close, because our eyes see angular size, not distance, not depth, just a glowing circle on a flat sky. But then comes the deeper measurement, the measurement that doesn't care what our instincts want. Light. Here is where the story cracks open. Light is the fastest thing we know. It moves at about 300,000 kilometers per second, about 186,000 miles per second. That number is so violent it almost feels fictional. But NASA and ESA engineers treat it like a clock, because once we use light, distance stops being a length. Distance becomes time, and the Earth-Moon gap has a signature time. A signal traveling at the speed of light takes about 1.3 seconds to go from Earth to the Moon, one way. So if we send a message, it takes 1.3 seconds to arrive, and the reply takes another 1.3 seconds to come back. That's roughly 2.6 seconds round trip, and suddenly the Moon stops being a place in the sky. It becomes a delay, a pause you cannot remove, not with better technology, not with faster computers, only by shrinking the universe, which we can't. This is what distance does. It imposes silence. Even a simple conversation becomes fractured. We ask a question, then we wait, then the answer returns like an echo from another world, and this creates a bigger problem, because if the Moon forces delay, then emergencies become something else entirely. On Earth, we are used to immediate response, a call, a siren, a door opening. But across 384,400 kilometers, 238,900 miles, there is no immediate. There is only waiting, and the Moon makes that reality unavoidable. Picture this. We shrink Earth down to a basketball about 24 centimeters, about 9.5 inches wide. Now we want the Moon in the right place, at the right scale. The Moon would be a ball about 6 centimeters, about 2.4 inches wide, roughly the size of a tennis ball. Where do we put it? Not across the room, not across the street. We place it about 7 meters away, about 23 feet away. That's like standing in your living room, holding the basketball in your hands, and putting the tennis ball all the way across a large room or down a long hallway. And that's just the Moon. Now imagine the space between them. Mostly nothing, not fog, not air, not darkness like a room. A near-perfect vacuum, a gap that doesn't feel like anything until you try to cross it. That is the first honest portrait of space, not planets, not stars. The emptiness between. And the Moon is the first time we're forced to look at that emptiness without flinching. This is why Apollo was not just exploration, it was exposure. It was the first time human beings lived inside a distance too large for human instincts. When NASA sent Apollo crews to the moon, they didn't just leave Earth, they left immediacy. They left the comfort of being reachable. Because once you are that far away, help is not a helicopter. It's not an ambulance, it's not even a plane. Help becomes physics, fuel budgets, trajectories, life support margins, minutes measured like heartbeats. And the isolation wasn't poetic, it was operational. If something failed, mission control could not simply take over. They could advise, they could calculate, they could guide. But the crew still had to do it, alone, inside a sealed machine, surrounded by vacuum. And the farther they travelled, the clearer the truth became. Distance is not a background feature of space. Distance is the enemy that never sleeps. This is why Apollo 13 still feels like a cosmic nightmare. A damaged spacecraft, a crew far from home, and the only path back was through a vast, silent geometry. The farthest humans have ever travelled from Earth happened during the Apollo era. Just over 400,000 kilometres, about 250,000 miles at the far side of their loop. That is the most physically isolated our species has ever been. No human before, no human since. Not because we don't have the technology to reach high orbit, but because nothing else has carried us that far away from Earth's immediate reach. And this raises another question. If the moon is already this distant, why does it still feel like a neighbour? Our minds confuse visibility with nearness. We see the moon in crisp detail. We see its craters, its shadows, its calm face. So we assume it must be close. But clarity is not closeness. Clarity is just brightness and perspective, and the fact that the moon is large enough to be seen easily. In reality, the moon is so far away that it already breaks our normal ways of thinking. On Earth, when something is truly far, it looks small. But the moon doesn't look small, so our instincts misfile it. They place it in the category of reachable. Yet the moment we try to treat it like a nearby destination, the numbers become brutal. Even travelling at the speed of a rifle bullet, fast by human standards, the trip would still take days, and at the scale of normal vehicles, it becomes ridiculous. Distance does not care what feels possible. Distance only cares what is. And this is the gateway moment. The moon is the first distance that exposes a hidden truth. Space is not up there. Space is not a thin layer above our atmosphere. Space is a vast separation where even our closest neighbour is beyond the reach of instinct. And if you could stand on the moon right now, alone on that grey dust, and speak into a radio, you would hear your own words return with a pause, not because the signal is weak, not because the technology is old, but because the universe inserted time between you and home. You would say, "Can you hear me?" And then there would be silence. A silence with a measured length. A silence built out of distance. And in that pause, you would feel what the moon truly is. Not an object, a separation. So what does the moon teach us? It teaches us that our intuition is useless beyond a certain scale. The moon forces a new kind of understanding. 384,400 kilometers, 238,900 miles of separation, 1.3 seconds one way at the speed of light, roughly 2.6 seconds for a question and an answer to complete a round trip, a distance so large that help becomes planning, not response, and the moon does something else. It sets the tone for everything that follows, because the moon is not the dramatic part of the universe, it's the gentle introduction, the calm opening door. If this is what near looks like, then far is going to be catastrophic, and that's why the moon is the gateway distance. Not because it's the first place we visited, but because it's the first place that proves a terrifying idea. The universe is not built around our sense of scale. The universe is built around space, and space is mostly emptiness. This is where the story shifts. If the moon is already distant enough to fracture our instincts, What happens when we widen the frame to include the planets? Because the shocking truth is not that the solar system is huge, it's that it is mostly empty. Textbooks draw the planets like neighbours on a page, but in reality they are islands separated by oceans of nothing. And once we step beyond the moon, we don't just meet bigger distances, we meet a new kind of emptiness, where distance becomes the main character. When we picture the solar system, we picture a crowded neighbourhood. Planets lined up like beads, orbits drawn like neat rings, everything close enough to feel connected. But that image is a lie we inherited from diagrams, because the solar system is not a collection of worlds, it's a collection of gaps, vast, cold separations so large they don't feel real, until we try to cross them. And this is where everything changes, because the true shape of the solar system isn't drawn by the planets. We learned the solar system from drawings, and drawings have a problem. If you draw the planets to the right sizes, you can't fit the distances on the page. If you draw the distances correctly, the planets become invisible specks. So most diagrams choose a third option. They compress reality until it looks comfortable. But space isn't comfortable. Space is an arena where next door can mean tens, hundreds, thousands of millions of kilometers. And here's the strange part. Even when we know that, our instincts still imagine the planets as close, because our brains were built for forests, streets and horizons, not for interplanetary void. This created a bigger problem, because the moment we leave the moon behind, we enter a region where our old language collapses. Far, near, close by. Those words stop working. Picture this. We shrink the sun down to the size of a large beach ball, bright, loud, dominating the room. Now, Earth at the right scale becomes a peppercorn, a tiny black dot. Where do we place it? Not a few steps away. We place it about 26 meters away, about 85 feet away. That's across a small park, across a long hallway, across a space that already feels oddly excessive for something that looks so near in the sky. Now we look for Jupiter. Jupiter becomes a grape, but it doesn't sit near the peppercorn. It sits farther, hundreds of meters away in this scale model. And Neptune? Neptune becomes another small bead, placed so far away that the model stops feeling like a display and starts feeling like a search. And in between those tiny objects, nothing, just open space. That's the solar system's true architecture, not planets orbiting a star, islands, separated by oceans. Here's the problem. Kilometers and miles are too quiet. They don't carry emotional weight unless we translate them into something we can feel. So astronomers use a more honest ruler. They use light, because light doesn't negotiate. Light doesn't care about our instincts. Light turns distance into time, and the solar system has its own terrifying clock. From the sun to Earth, sunlight takes about 8 minutes and 20 seconds to arrive. Think about that. Every sunrise we've ever seen is already old when it touches our skin. But then the distances stretch. Sunlight reaches Mercury in about 3.2 minutes. It reaches Venus in about 6 minutes. It reaches Mars in about 13 minutes. So even in the inner solar system, our so-called local area, light is already spending minutes just crossing space, and then we step outward, and the clock gets heavier. From the Sun to Jupiter, sunlight takes about 43 minutes. To Saturn, about 80 minutes, 1 hour and 20 minutes. To Neptune, about 4 hours. That means Neptune doesn't just orbit far away. Neptune exists in a different time zone of reality. When Neptune sees the Sun, it sees the Sun as it was hours ago. And this wasn't the only twist, because sunlight is still the easy version. Communication is worse. Mars is the planet we talk about, like it's around the corner. But the distance between Earth and Mars breathes and stretches as both worlds move in their orbits. NASA describes it plainly. Earth and Mars can be as close as 54.6 million kilometers, about 33.9 million miles, which is about 3 minutes at light speed, or as far as 400.2 million kilometers, about 248.7 million miles, which is about 22.4 minutes at light speed. That means when we speak to Mars, we don't speak in real time. We speak into delay. We send a command, then we wait again. And if something goes wrong, we don't react. We hope. This is what distance does. It turns action into anticipation. It turns control into prediction. And once we accept that, the solar system stops feeling like a set of destinations and starts feeling like a chain of isolated outposts. Now let's go to the edge of the familiar map. Pluto. Pluto is often treated like the faraway icon of the solar system, but Pluto reveals something more disturbing than far. Pluto reveals isolation. On average, Pluto is about 5.9 billion kilometers, about 3.7 billion miles from the Sun, and sunlight takes about 5.5 hours to reach it, 5.5 hours. That's the length of a long flight. A long drive across country is a whole day's chunk of life, just for light to arrive. And yet, Pluto is not the end. Pluto is not the wall. Pluto is simply a small world sitting inside a darkness so wide that our minds struggle to even assign it shape. Because beyond Pluto isn't a line. It's more distance, more emptiness, more silence. And this raises another question. If Pluto is only hours away by light, what does it mean to truly leave planetary space? This is where the story gets unsettling. Humans have launched thousands of spacecraft, but only a handful have actually gone into the outer dark. The Voyager probes are different. NASA's Voyager missions launched in 1977. They flew past the giant planets, and then they kept going into a region where the sun's influence weakens and the interstellar environment begins. NASA says both Voyager 1 and Voyager 2 have reached interstellar space. Voyager 1 crossed into interstellar space in August 2012. Voyager 2 entered interstellar space in 2018. But then comes the part most people miss. Even now, they have not left the solar system in the deeper gravitational sense. NASA explains that while the probes have left the heliosphere, they have not yet left the solar system and won't be leaving anytime soon, because the boundary is considered beyond the Oort cloud, and the Oort cloud is not nearby. NASA describes estimates that it begins around 1,000 times the Earth-Sun distance and could extend to 100,000 times that distance. So even the farthest machines we've built are still traveling through the Sun's long, fading reach. That's the truth Voyager carries. Not just a golden record, a message of scale. Voyager is moving fast by human standards. It crosses millions of kilometers with patient persistence. But cosmic distance makes speed feel like a joke. Voyager launched in 1977, decades of flight, and still it has only reached the beginning of interstellar space. Now place that journey against human history. If a Voyager-like craft had launched when the Roman Empire was still standing, it would still be crawling through the sun's outskirts today. If it had launched when the pyramids were young stone, it still wouldn't be anywhere near another star. This isn't because our engineering is weak, it's because space is monstrous. Distance doesn't just slow us down, distance humiliates the idea of arrival. And if you could stand in a spacecraft somewhere between the worlds, far from Earth, far from Mars, you wouldn't feel like you're traveling. You would feel like you're suspended, a small warm cabin surrounded by an ocean that has no surface, no scent, no wind, no sound, just darkness and a few bright points that don't reveal how far away they truly are. You would look out and see the planets as lights, not places, and you would finally understand why the solar system feels empty, because it is. So what have we uncovered? The solar system doesn't scale down into something visual, it breaks visibility. Light takes minutes just to cross the inner region near Earth. Light takes hours to reach the outer planets, 4 hours to Neptune. Pluto isn't a distant finish line. Pluto is a small world marooned in a widening gap, 5.9 billion kilometers, 3.7 billion miles, 5.5 hours of sunlight away. Voyager is proof that even our fastest long-term journeys barely touch the true scale, and even then, they're still inside the sun's extended domain. This is the cosmic reality hiding behind every neat diagram. The solar system is mostly empty, not metaphorically, literally. And that emptiness is not just background, it is the defining structure. And now we hit the next fracture. Because once we start thinking in light minutes and light hours, kilometers begin to feel useless. They don't carry meaning, they don't carry intuition, they become a pile of numbers we can't emotionally hold. So the universe forces us to adopt a new language, a language built out of light itself. And once we accept that measuring stick, we're going to realize something even more disturbing. We never see the universe as it is. We only see it as it was, delayed by distance. And that is where the real story begins. We keep trying to measure the universe the way we measure our lives, in kilometers, in miles, in road distances. A few thousand kilometers feels like far. A few thousand miles feels like the other side of the world. But then we look up, and those words collapse. Because beyond the planets, distance stops being a number we can hold. It becomes something colder, something more disturbing. It becomes time. And that is why astronomy had to invent an honest ruler. Not a ruler made of metal, not a ruler built for maps, a ruler made of light. Because light doesn't care what feels near. Light tells the truth, even when the truth is uncomfortable. Kilometers and miles are perfect for Earth. They fit roads, oceans and continents. They fit the scale of human work. But the solar system already pushes them to the edge. We say 100 million kilometers and our minds go quiet. We say 1 billion kilometers and meaning evaporates. Not because the numbers are wrong, but because our intuition has no place to store them. So scientists built a different language, one that forces understanding. They didn't ask, how far is it? They asked, how long does light take to get there? Because time is something our bodies understand. We feel seconds, we feel minutes, we feel hours. And the universe, cruelly, is built on delays. This created a bigger problem. Because once we start thinking in light, we realize we are never looking at the universe now. We're always looking at it late. Light moves at about 300,000 kilometers per second, about 186,000 miles per second. That speed is so staggering it feels impossible. But for NASA, for ESA, for every telescope team on Earth, it is the foundation of reality. Because light is not just illumination. Light is information. Every image of a planet is a message delivered by photons. Every star you see is a signal that survived a journey through emptiness. And here's the disturbing part. Even at the fastest speed in the universe, light still takes time, which means the universe is structured around delay, not opinion, not interpretation, delay. So when astronomers measure distance, they aren't measuring how far, they're measuring how late. And that's when the universe becomes unsettling. Let's start with the smallest honest unit. A light second is the distance light travels in 1 second. That's about 300,000 kilometers, about 186,000 miles. In human terms, it's violent. In 1 second, light could circle Earth more than 7 times. But this is the first twist. A light second is still tiny compared to the solar system. Even the space between Earth and the Moon is more than 1 light second. It's about 1.3 seconds one way. So, the moment we step off Earth's surface, even our nearest destination is already measured in light time. And this wasn't the only shift, because then we reach the scale where the numbers start to feel like weather systems, minutes. A light minute is the distance light travels in 1 minute. That's about 18 million kilometers, about 11 million miles. Now, we're no longer talking about a space between objects. We're talking about a region, a slice of the solar system. And this is where our everyday intuition begins to fracture, because our most important example, our most intimate example, is sitting in the sky every day. The sun. Sunlight takes about 8 minutes and 20 seconds to reach Earth. Let that settle. The warmth on our skin is old. The light that fills our mornings left the sun more than 8 minutes ago. If the sun, right now, were to vanish, the sky would not immediately go dark. The world would keep shining. Birds would still fly. Clouds would still glow. And we would not know the truth for 8 minutes. That's how light reveals reality, not as it is, but as it was. And once we accept that, we begin to realize something deeper. Distance is not just separation. Distance is the gap between cause and awareness. Picture this. We're standing outside holding a phone, and somehow, impossibly, the sun can answer. We ask one simple question, "Are you there?" Then we wait. 8 minutes, 20 seconds. Only then does the reply arrive. Not because the sun is slow, not because the connection is weak, but because space itself has inserted time between us. Now imagine trying to do anything urgent through that delay. Imagine trying to steer. Imagine trying to warn. Imagine trying to save. This is what light time means. It means the universe has no real-time mode, and that truth doesn't stop at the sun. It only gets worse. A light hour is the distance light travels in 1 hour. That's about 1.08 billion kilometers, about 671 million miles. Now we're talking about distances that crush our sense of nearby. Because once we reach light hours, the solar system stops feeling like a family of planets and starts feeling like scattered outposts. And here's the strange part. The farther you go from the sun, the more the universe feels like it's running behind. Out there, the sun is not a present object. It's a delayed influence, a memory traveling through space. And that changes how we understand everything, because if sunlight is delayed, then every image we capture is delayed too, which means astronomy is not just looking outward. Astronomy is looking backward. And when you look at the sun, when you feel its heat, when you watch a sunset bleed into the horizon, you are not experiencing the sun now. You are seeing the sun as it was more than 8 minutes ago. That means you have never, not once in your life, seen the sun in real time. You have only seen its past. And if that is true for the closest star, then what do you think is happening when we look at stars that are light years away? This raises another question. If distance is time, then what exactly are we seeing when we observe the universe? Kilometers and miles are static. They describe space as a place you can cross. But the cosmos is not experienced as space. It is experienced as information arriving late. So astronomers speak in a different language. Light seconds, light minutes, light hours. Not because it sounds dramatic, but because it is accurate. It is the only way to describe what the universe is actually doing to us. When we observe, we are receiving messages. When we measure, we are timing arrivals. When we map the cosmos, we are building a timeline disguised as a map. And this is why the universe feels like a mystery. Because we never receive the full story at once. We receive fragments, delivered across delay. This is where science becomes almost philosophical. Because astronomy is not like geology. We can touch rocks. We can drill into Earth. We can test samples directly. But we cannot touch most of what we study in space. We can't visit distant stars. We can't scoop material from a galaxy millions of light years away. So astronomers do something both simple and profound. They read the light, they measure its brightness, they break it into colors, they track how it shifts, they turn photons into evidence, they take a delayed signal and reconstruct a reality. This is how we know what stars are made of. This is how we know how hot they are. This is how we learn how fast objects move. Because light is not just a glow, it carries fingerprints, it carries history, it carries violence, and it carries time. But then comes the more unsettling part. Delay doesn't just affect our measurements. Delay shapes the universe we can ever know. Because there is a hard boundary to information, a horizon made of time itself. And we're going to face that later. For now, we're building the first truth. The universe is not out there. The universe is back then. So this is what light reveals. Kilometers and miles fail beyond a certain scale because they don't connect to human meaning. Light seconds make nearby space measurable, about 300,000 kilometers, 186,000 miles per second. Light minutes reshape the inner solar system, about 18 million kilometers, 11 million miles per minute. Light hours swallow the outer regions, about 1.08 billion kilometers, 671 million miles per hour. And the Sun, our closest star, is always seen 8 minutes and 20 seconds late. This isn't a poetic metaphor, it's the operating system of reality. Einstein understood that the universe does not hand us absolute now, it hands us signals, and those signals travel through space at a finite speed. So every observation is also a delay. Every measurement is also a look into the past. And once we accept that, we can no longer pretend that nearby means what we thought it meant, because if light takes 8 minutes to reach us from the Sun, then the nearest star beyond the Sun is going to feel like something else entirely. So, here's the cliffhanger that should make us uneasy. If the Sun is already 8 minutes away by light, then what is the next star? How long would its light take to reach us? How long would a message take? How long would rescue take? The answer is not a little farther. The answer is a scale jump so violent it breaks language, because the nearest star is not a neighbor. It is a separate world across a gulf so wide that even our fastest machines barely make sense inside it. And once we step into that gulf, the universe stops feeling big. It starts feeling unreachable. We hear the phrase all the time, the nearest star. It sounds comforting, like the universe has neighbors, like if we just go far enough, we'll arrive at the next light on the street. But this is where everything changes, because the nearest star beyond our Sun is not nearby. It is separated from us by a gulf so wide that the word distance becomes too small to carry it. And once we truly face that gulf, we begin to understand the real shape of the universe, not as a place filled with objects, but as a place defined by separation, by emptiness, by silence that grows stronger the farther we look. The closest star to our solar system is Proxima Centauri. NASA describes it plainly, about 4.25 light-years away, roughly 40 trillion kilometers, about 25 trillion miles. Those numbers are not meant to impress us. They're meant to correct us, because our eyes keep whispering that the stars are up there. But Proxima Centauri is not up there. It is elsewhere. And to understand what 4.25 light-years means, we need the only measuring stick that doesn't lie: light. NASA defines a light year as the distance light travels in 1 year, about 9.46 trillion kilometers and 5.88 trillion miles. So when we say Proxima is 4.25 light-years away, we're saying its light needs more than 4 years to reach our eyes, which means when we look at Proxima tonight, we are seeing it as it was back in late 2021. Not now, not live. A delayed signal crossing interstellar emptiness. And that delay is the first emotional weight of interstellar space. We've already learned to think in light minutes and light hours inside our own solar system. Sunlight reaches us in a little over 8 minutes. That already feels unsettling. But Proxima Centauri is not 8 minutes away. It's over 4 years away, and the jump in scale is brutal. NASA also notes Proxima is about 268,770 astronomical units away, meaning it's roughly 268,770 times farther than Earth is from the Sun. That number matters because it exposes the lie in our mental pictures. In our minds, the solar system feels large and the stars feel like the next step beyond it. But the truth is harsher. The solar system is a small island, and the nearest star is not the next island over. It's across an ocean so wide our maps stop working. And this created a bigger problem, because it means the space between stars isn't more space, it's a different category of emptiness. Picture this. We scale Earth's orbit down to something we can hold. We set the distance from Earth to the Sun, the astronomical unit, to just 1 meter, about 3 feet. One simple step, 1 meter. Now we ask where Proxima Centauri goes in this scale. Not across the room, not across the street. Proxima Centauri would be about 269 kilometers away, about 167 miles away. That's not a model anymore. That's a drive between cities. And in between those 2 meters of meaning, there is almost nothing. No planets, no warm light, no structure we can live in, just a widening, cold separation. This is what stellar neighborhood actually means. Not closeness, just the absence of anything closer. And if you aimed a radio dish at Proxima Centauri and said one word, hello, that word would travel for 4.25 years before it reached anything that could hear it. And if something answered immediately, you would wait another 4.25 years for the reply. That's about 8.5 years just to complete a single question and a single response. Not because the signal is weak, not because the equipment is old, but because the universe inserts time between islands of matter. Distance doesn't just separate us, distance delays reality. Now we bring in the second truth. Light can cross that gulf in 4.25 years, but we cannot. NASA reports Voyager 1 is moving at about 17 kilometers per second, about 38,000 miles per hour. That speed is staggering in human terms. At that speed, we could cross the entire width of Earth in minutes. We could cross continents like they were thin shadows. But interstellar distance doesn't care. Using NASA's distance to Proxima Centauri and Voyager's speed, the math becomes almost cruel. At Voyager 1's pace, a journey to Proxima would take roughly 75,000 years. 75,000. That is not a long mission. That is a different era of humanity. 75,000 years ago, our species was still living deep in prehistory, long before agriculture, long before cities, long before written language. If a probe had launched toward Proxima Centauri when the first humans were painting on cave walls, it still wouldn't be there, and this wasn't the only twist. Even our fastest human-made speed doesn't rescue us from this truth. NASA says the Parker Solar Probe can reach about 700,000 kilometers per hour, about 430,000 miles per hour, the fastest speed ever achieved by a spacecraft. Even if we could sustain that extreme speed in deep space, without slowing, without fuel limits, it would still take on the order of thousands of years to reach Proxima. Thousands, not decades, not lifetimes, civilizations. So when we say the nearest star, we are not describing a destination, we are describing a boundary, a reminder that our species is still trapped on the inside of its local island. And now the emptiness becomes personal. We imagine stars like streetlights, close enough that the space between them feels filled. But in the solar neighborhood, the average distance between stars is measured in multiple light years. A university astronomy lecturer from Ohio State describes the local solar neighborhood as extremely sparse, noting an average distance between stars of about 6 light-years and only a few stars per 1,000 cubic light-years. 6 light-years. That means our nearest neighbor star system being about 4¼ light-years away isn't unusual. It's the rule. Stars do not cluster like homes. They scatter like isolated fires across a dark plane. And this is why interstellar travel isn't difficult in the way climbing a mountain is difficult. It's difficult in a colder way. There's nothing to grab onto. No stepping stones, no halfway point. Just the long, empty between. This is the part that quietly changes us. Inside the solar system, we still feel connected. We can imagine rescue. We can imagine return. We can imagine a signal arriving soon enough to matter. But between stars, the emotional texture changes. Out there, even communication becomes slow. Even knowledge becomes delayed. Even hope becomes stretched across years. And this is why scientists speak about interstellar space with such careful language. Not because it's romantic, because it's honest. Einstein taught us that information cannot travel faster than light. That limit doesn't just shape physics, it shapes loneliness. It guarantees that every civilization, every world, lives inside its own time bubble. And even if the universe is full of light, distance ensures that light rarely touches. So what have we learned from Proxima Centauri? The closest star beyond our Sun is about 4.25 light-years away, around 40.2 trillion kilometers, 25 trillion miles. A light-year is the distance light travels in a year, about 9.46 trillion kilometers, 5.88 trillion miles. Voyager 1 moves about 17 kilometers per second, about 38,000 miles per hour. And at that pace, reaching another star would take tens of thousands of years. The stellar neighborhood is not a neighborhood. It's a desert, with stars spaced light-years apart. This is the first time the universe forces us to admit something uncomfortable. Our solar system is not the opening act to the stars, it's a tiny enclave, a warm island, and beyond it begins a scale of separation that treats our technology like a fragile spark. And now the scale becomes inevitable. If one neighboring star already feels unreachable, what happens when we stop thinking in single stars and start thinking in galaxies? Because a galaxy isn't a handful of suns. It's a structure so wide that it can swallow light for tens of thousands of years. And inside that structure, stars aren't close. They are still separated by emptiness, just on a scale so enormous it changes what space even means. And once we step into that next frame, we'll realize something even more disturbing. A galaxy looks bright, but most of it is darkness. On a clear night, the Milky Way looks like a smear of pale light across the sky, a soft scar, a quiet river, close enough to feel familiar. But that comfort is an illusion, because that mist is not mist. It is the combined glow of an impossible number of stars, stacked behind each other, so far away that our eyes can't separate them anymore. And here's the disturbing part. If we could step outside our galaxy and look back at it, if we could see the whole structure at once, our home would not feel like a neighborhood. It would feel like a continent of light, surrounded by an ocean so empty it turns distance into a kind of silence, and we don't even notice we're inside it. We talk about the Milky Way like it's an object in the sky, like it's something out there, but we're not looking at it from the outside. We're inside it, buried in its disk, trying to understand its shape from the inside of the shape. It's like living in a city of fog and trying to map the skyline by staring into the haze. So our brains do what they always do. They compress, they flatten, they simplify. They turn a three-dimensional structure into a thin, glowing band. And that band feels close, because our vision is designed for trees, faces, roads, not for a galaxy. To even speak honestly about this place, we have to change our language, because kilometers and miles collapse under the weight of a galaxy. So astronomers use a unit that feels almost poetic, but it's brutally literal. A light year is the distance light travels in one Earth year. That's about 6 trillion miles, or 9 trillion kilometers. Not because scientists love grand numbers, because the universe forces them to speak in grand numbers. Now take that light year and multiply it by 100,000. That's the approximate span of our galaxy, about 100,000 light years across, which means if light started at one edge of the Milky Way and raced across at the fastest speed anything can move, it would take about 100,000 years to reach the other side. 100,000 years. That number sounds abstract until we anchor it to us. When that light began its journey, human civilization did not exist. No cities, no writing, no empires. Agriculture hadn't begun. History hadn't begun. Our species was still young. We were still learning how to survive the night. And that's the first crack in the illusion. Inside our own galaxy, distance is already time. Imagine this. You're standing at one end of a long, dark hallway. Along the hallway are thousands of tiny lights, like little night lights, spaced far apart. If you look sideways, you might only see a few. But if you look straight down the hallway, all those lights stack on top of each other. They blur into a single glowing band. That's what the Milky Way is doing to our eyes. We're not seeing more stars because the galaxy is crowded. We're seeing more stars because we're looking through a long corridor inside the disk, through layers of distance we can't feel. Brightness becomes a trick of alignment. The band looks dense, but the truth is colder. Astronomers estimate our galaxy holds somewhere between 100 and 400 billion stars. That number sounds like congestion, like traffic, like crowding. But then, the universe reveals the twist. Even with hundreds of billions of suns, the Milky Way is still mostly empty space. In our local region, the solar neighborhood, the overall number density is about 1/10 of a star per cubic parsec. That's technical language, but the meaning is simple. Stars are not packed shoulder to shoulder. They are scattered, separated by distances so large that even nearby becomes a kind of exile. Our closest neighbouring star system is more than 4 light years away. And 4 light years is not a little farther. It's 4 years at the speed of light. 4 years of emptiness. If our sun were a single porch light in a dark countryside, the nearest porch light would be so far away that we wouldn't even see it most nights. This is why the galaxy feels like a glowing cloud, yet behaves like a desert, because emptiness is doing most of the work, and our place inside this structure is not special, it's just located. Our solar system sits about 26,000 light years from the galaxy's centre, not near the bright heart, not out at the faint edges, somewhere in the middle, along a spiral arm, moving with everything else. And we are not standing still. Our sun is orbiting the galactic centre, and one full trip takes on the order of a few 100 million years, about 250 million years, which means the last time we were in this same region of the Milky Way, Earth was not modern, it was ancient. The world was ruled by life forms that didn't know the sky had a name. Our entire recorded history, every kingdom, every war, every language, fits into a fraction of a single orbit. So when we say we live in the Milky Way, we should hear what that really means. We are passengers on a slow, silent carousel, turning through a structure so vast that time itself becomes small. And if you've ever stood under a truly dark sky, far from city lights, then you felt it without realizing. That pale band overhead is not a backdrop. It's the direction of the galaxy's plane. It's the long interior of the disk, where our line of sight cuts through the greatest depth of stars. You're not just looking up, you're looking along, and suddenly The night stops being a ceiling and becomes a tunnel. But even this view is incomplete, because between us and the galactic center, there are vast clouds of dust and gas that block our sight in visible light. So for centuries, we didn't even know what the center truly was. We had to invent new eyes, radio telescopes, infrared surveys, space missions, ESAs. Gaia mission began mapping the positions and motions of enormous numbers of stars, turning the Milky Way into data, into structure, into something measurable instead of mythical. Because galaxies don't reveal themselves easily, they hide behind distance, they hide behind dust, they hide behind the limits of the human senses, and still we keep measuring, because scientists hate mysteries. But the Milky Way is a mystery built out of scale. So what have we really uncovered? We've uncovered the uncomfortable truth that even inside our home, we are separated from almost everything by vast, cold nothingness. A galaxy is not defined by its stars. It's defined by the space between them. A galaxy is an island of light, and most of that island is uninhabited darkness. And that should feel unsettling, because it means our instincts are wrong. We look at the Milky Way and feel surrounded. But the physical reality is the opposite. We are isolated, inside a structure that only looks crowded because we're staring through its depth. But then the universe does something cruel. It asks the next question. If one galaxy can be 100,000 light years wide, if light needs 100,000 years just to cross our own island, then what is the distance between islands? Because the nearest major galaxy, Andromeda, is about 2.5 million light years away. 2.5 million. That's not a step outward. That's a leap into a void so vast it makes our entire galaxy feel small. And this is where the story fractures again. Because the Milky Way isn't floating in a crowded universe. It's drifting in a dark ocean, with other galaxies scattered so far apart that even collisions take billions of years. And once we face that distance, we stop thinking of the universe as a place filled with objects, and start seeing it for what it really is, a cosmos built out of separation. And that's when the real problem appears. Look up on a clear night and the sky feels intimate, a bowl of darkness, a handful of stars, a few bright smudges. But then, one of those smudges breaks the spell, because that faint pale streak in the constellation Andromeda is not a cloud. It's not a nearby fog. It's an entire galaxy, a separate island of hundreds of billions of stars, hanging outside our own. And here's the disturbing part. It's close enough that, under dark skies, we can see it with our unaided eyes. But it's also so far away that the light reaching us tonight began its journey about 2.5 million years ago. That contradiction, visible yet unreachable, is where our sense of distance fractures. Because once we accept Andromeda is real, we're forced to face what lies between galaxies. And what lies between galaxies is not space, it's distance, cold, silent, structuring everything. And this is where everything changes. They call it the Andromeda Galaxy. Astronomers label it Messier 31. It's the nearest large spiral galaxy to the Milky Way. And nearest sounds comforting, except nearest means about 2.5 million light years away. That number is clean, but our minds don't feel it, so we translate it into something our bodies understand. A light year is how far light travels in 1 year, moving at about 300,000 kilometers per second, or about 186,000 miles per second. And now, the uncomfortable truth. At that speed, the space between our galaxy and Andromeda still takes 2.5 million years to cross. 2.5 million years ago on Earth, modern humans did not exist. Civilization was not a dream. The sky had never held a satellite. No city lights, no written language, no recorded history. The photons touching our eyes tonight left Andromeda before any human mind had ever wondered what the stars were. So when we look at Andromeda, we are not seeing a place, we are seeing a time, and that creates a new problem. If Andromeda is that far, what does it mean when astronomers say galaxies are neighbours? Now we step into one of the universe's strangest contradictions. Astronomers have measured that Andromeda and the Milky Way are moving toward each other, and that in roughly 4 billion years they are expected to merge. A collision between galaxies sounds like a cosmic catastrophe, a shredding, a violent impact, a sky on fire. But then, something almost impossible is true. When galaxies collide, the stars almost never hit each other, because galaxies are not packed like marbles. They're not solid objects. They're mostly empty. The average distance between stars is so enormous that even as two galaxies pass through each other, most stars simply miss. So the collision is not like two cars crashing. It's more like two swarms of insects crossing paths in a cathedral. Vast space between them, dark air, and near total silence. The real violence is not star against star. It's gravity against structure. It's tidal forces stretching galaxies, warping orbits, compressing gas clouds, triggering bursts of star formation in some regions, stripping material in others. A galaxy collision is often a choreography of emptiness, and this shatters our instinct again, because we've been trained by diagrams, bright planets lined up neatly, galaxies drawn like close neighbours. But the universe is not a cluttered room. It's a dark ocean where the islands are separated by distances so extreme that even when islands meet, most of what happens is nothing touching anything. And this wasn't the only one, because the Milky Way and Andromeda aren't alone out there. They belong to something larger. Picture this. Imagine a city at night, but the city is in a blackout. No streetlights, no glowing windows. Now imagine there are only a few lanterns spread across that entire city. One lantern is the Milky Way, another lantern is Andromeda. A third is the Triangulum Galaxy, and scattered around them, dozens of tiny candles, dwarf galaxies, small and faint, barely visible. That city is what astronomers call the local group, a gravitationally bound collection that includes the Milky Way, Andromeda, and many smaller galaxies, about 50 other systems, mostly dwarfs according to Encyclopaedia Britannica's description of galaxy groups. And here is the key. The local group is not defined by its members. It's defined by the space between them, and the gravity that still reaches across that space. Because gravity doesn't stop at the edge of a galaxy. It stretches, thin, patient, relentless, across distances that feel impossible. When Edwin Hubble helped reveal that galaxies are separate systems beyond the Milky Way, he didn't just expand the map. He ripped open our sense of scale, and today, with modern measurements, astronomers can track Andromeda's motion with enough precision to forecast a future merger, and they tie that motion to the unseen mass holding the local group together. Because here's what holds this neighborhood in place. Not just the stars, not just the gas, but a much larger, invisible structure. Astronomers infer that dark matter halos surround galaxies, and that the local group's dynamics, especially the Milky Way Andromeda system, reflect that hidden mass. We don't see dark matter the way we see stars. We see its fingerprints, the way galaxies rotate, the way clusters hold together, the way motion refuses to match visible mass. So when we say gravity operates across millions of light years, we're describing a force that doesn't need light. It doesn't need visibility. It only needs distance, and distance is the medium it rules. But this raises another question. If galaxies can be bound into groups by gravity, what does that mean for the shape of the universe itself? Is it just scattered islands? Or is there a hidden architecture? Now, let's do something unsettling. Imagine you could stand outside the Milky Way, not inside it, not under its stars, outside it, far enough away to see it as a whole. And then, You turn your head toward Andromeda. You would not see a nearby neighbor. You would see a separate universe of stars, floating at a distance so extreme that your entire species is younger than the light between you and it. And in that moment, the truth lands. Between galaxies, distance isn't a measurement. It's a barrier. It's isolation made physical. It is why, even in a universe full of galaxies, everything still feels quiet. But we're not done, because even 2.5 million light years is still local, and that is the most disturbing part of all. So what do we take from this? First, Andromeda proves that galaxies are not decorations on the same ceiling. They are separate realms. Second, collisions between galaxies reveal the universe's true nature, that even dramatic events are built out of emptiness. Third, the local group shows that gravity can stitch galaxies into communities across enormous distances, and that the universe has structure, not clutter. When we stop imagining the cosmos as crowded, we start seeing it as something colder and more honest, a small number of luminous islands held in place by invisible mass, separated by oceans so vast that our instincts collapse. And yet, we can still see Andromeda with our naked eyes, a galaxy that is not close, a galaxy that is not reachable, a galaxy that is, in human terms, almost outside time, which means the sky is not what it seems, because the farther we look, the more the universe becomes a museum of light, and that's where the story cracks open next. If Andromeda is 2.5 million light years away, and we can still see it with our eyes, then what happens when we look far beyond Andromeda? What happens when the light isn't millions of years old, but billions? Because out there, distance stops being geography. It becomes a time capsule, and once we open that capsule, we're forced to face the most disturbing truth of all. The farther we see, the less of the universe we're actually allowed to witness. We tend to think the universe is something we can eventually cover, like a landscape. If we build stronger telescopes, we'll see it all. If we wait long enough, we'll understand the whole map. But then the universe reveals a rule that feels almost cruel. We don't get to see everything, not because our technology is weak, not because our eyes are small, because reality has a speed limit, and because the universe has a past. So when we look outward, we are not looking across space. We are looking into an archive, a time capsule, sealed by distance, and the deeper we stare, the older the pages become. Observable universe sounds like a technical phrase, but it's a confession. It means the part of the universe that has had enough time to send us a message. The limit isn't our instruments. The limit is physics. No signal can travel faster than light, and the universe has only existed for about 13.8 billion years, so there are regions so distant that their light has not reached us yet. They may exist, but they are outside our horizon, outside our evidence, and this is important. Observable does not mean visible with our best telescope. It means reachable by information at the speed of light. That distinction should feel unsettling, because it means the universe is not just large, it is partially inaccessible by design. Astronomers have estimated the size of the observable universe in a specific way. Not how far the light travelled, but how far away those regions are now, after billions of years of expansion. In that co-moving sense, the distance to the edge is about 46.5 billion light years in every direction, meaning a diameter of about 93 billion light years. Read that again slowly. 93 billion light years. And here's the twist that makes people feel like physics is cheating. If the universe is about 13.8 billion years old, why isn't the radius just 13.8 billion light years? Because while the light was travelling, space was expanding. The destination kept moving away. So a photon can travel for 13.8 billion years and still be arriving from a region that is now tens of billions of light years away. This is where our intuition collapses. Not because we're unintelligent, because our brains were built for distances that stay put. Now we face the deeper truth. Every telescope is a time machine. Light takes time to arrive, so distance automatically becomes history. When we look at the moon, we're seeing it a little more than a second in the past. When we look at the sun, we're seeing it minutes in the past. But when we look at galaxies millions or billions of light years away, we're watching the universe as it used to be. Not metaphorically, literally. NASA describes the cosmic microwave background, the CMB, as light that originated about 380,000 years after the Big Bang, when the universe cooled enough to become transparent. And that same light is observed today, stretched by expansion into a cold glow around 2.7 Kelvin. So the oldest light we can see is not from a star. It's from the moment the universe stopped being opaque, the moment the fog lifted. That light has been travelling almost the entire age of the cosmos to reach us. And when we map it, we are not just seeing far, we are seeing early. Imagine this. We walk into a massive library in the dark, and the only way to read is by waiting for a single slow messenger. Each shelf is farther away, and the messenger can only run at one fixed speed. So the books on the nearest shelf arrive quickly, almost instantly. They feel present. But the books on the far shelves arrive years later, then centuries later, then millions of years later, and at some point, the shelves become so distant that no book has ever arrived at all. That's the observable universe. It's not a border made of walls, it's a border made of time, a horizon made of delayed information. Now we step into the most disturbing part. Even within the observable universe, distance is not stable. While light is travelling, the universe is expanding, and that expansion stretches the space the light must cross. So when we say the CMB has been travelling for 13.8 billion years, we also say that the matter that emitted it is now much farther away than 13.8 billion light years. Astronomers calculate that the edge of the observable universe is about 46.5 billion light years away today, in that comoving sense, which means distance isn't just how far, it's also how the universe changed while the message was in transit. And this creates a deeper mystery. If the universe keeps expanding, does the observable universe grow? Do we get to see more over time? Or does expansion steal regions away faster than their light can ever reach us? We can feel the tension building already, because the universe is not just big, it is dynamic. And if you've ever stared into a deep field image, Hubble, or NASA's James Webb Space Telescope, then you felt it without the math. You're not looking at a lot of galaxies, you're looking at a timeline. Some of those galaxies are seen as they were billions of years ago, because their light has been crossing the cosmos for most of the universe's existence. So, in a single glance, you can hold more history than any museum on Earth. And the unsettling part is this. We don't just learn about the past, we see it. The universe forces us to witness time. So what does time capsule really mean? It means the observable universe is layered, like tree rings, like ice cores, like sediment beneath an ancient city. Closer regions show us recent cosmic history, galaxies shaped like they are now. Farther regions show us galaxies when the universe was younger, hotter, denser, still assembling. And at the farthest edge, we reach the CMB, a snapshot from the early universe, around 380,000 years after the Big Bang, before stars and galaxies as we know them had fully taken over. This is why astronomers don't just measure distance, they measure look-back time. Because distance is a record, every photon is evidence, every beam of light is a historical document that took an unimaginably long journey to reach our eyes. And the observable universe is the total collection of those documents, everything that had time to arrive. And now, we have to say it clearly, we do not see the universe as it is right now. We see a stitched-together mosaic of different eras. Near objects are seen almost as they are. Far objects are seen as they were long before Earth had modern life. And the farthest light we see is the universe's own afterglow. So our map of the cosmos is not a single moment, it's a layered memory, which means the universe isn't just vast in space, it's vast in time. But then the universe has one more twist. If the observable universe can be 93 billion light-years wide today, even though the universe is 13.8 billion years old, then distance is not the simple thing we want it to be. It's not a fixed ruler, it's a moving target. Space itself expands, while the light is still on the way. And that raises the next question we can't avoid. If space can stretch distance while light is traveling, how do astronomers measure anything at all? How do we translate redshift into distance? How do we speak about farther when the universe is changing under our feet? Because the moment we accept expansion, distance stops being a place and becomes an evolving process. We've been taught to picture distance as something fixed, a clean number, a straight line, a ruler laid between 2 points. But the universe refuses to behave like that, because while light is travelling, the space it's travelling through is changing. Not because the galaxy is sprinting through space like a bullet, but because space itself is stretching, quietly, relentlessly, pulling everything apart in a way our instincts were never built to sense. So we have a problem. If the universe is expanding while the message is in transit, then what does distance even mean? And this is where everything changes, because once we step into expansion, distance stops being a place and becomes a moving target. When we say the universe is expanding, most of us picture fireworks, galaxies exploding outward from a central point. But there is no center we can point to. There is no cosmic outside they're rushing into. What we're describing is more unsettling than that. It's this. The fabric of space itself is stretching, and as it stretches, the distance between galaxies grows, even if they're not firing engines. This is the difference between a car driving away from us and the road beneath both of us silently lengthening. One feels familiar, the other violates intuition. And yet, this idea isn't poetry, it's measurement. It's what Edwin Hubble's observations forced onto astronomy. When they saw distant galaxies were redshifted, their light pulled toward longer, redder wavelengths. And that redshift wasn't just a colour change, it was a confession. Here's the strange part. In an expanding universe, farther galaxies don't just recede more, they recede faster. That sounds like a galaxy is accelerating away from us like a spacecraft. But it's not the galaxy doing something special, it's the space between us. There's simply more space to stretch. Picture this. Imagine a long strip of soft rubber, like a stretchy exercise band lying on the floor. We draw dots on it with a marker, one dot near our hand, one dot far away. Now we stretch the band. The dot near us moves a little, but the dot far away moves much more. Not because the far dot tried harder, not because it had some secret engine, but because there was more rubber between us and it, more material available to stretch. That is the universe. The farther the galaxy, the more expanding space lies between us. So, its recession rate appears larger, and this is why our intuition fractures, because our brains grew up inside stable rooms, stable roads, stable distances. We were never designed to live in a geometry that changes while we look at it. Scientists summarize this stretching with a number called the Hubble constant, the expansion rate today. It's usually described like this. For every megaparsec of distance, about 3.26 million light-years, space expands so that galaxies recede roughly 70 kilometers per second. 70 kilometers per second. That's about 43 miles per second. At that speed, we could cross a large city in a blink. We could circle Earth, about 40,000 kilometers, 25,000 miles, in roughly 10 minutes. And yet, that speed is not a ship's speed. It's the rate at which space adds separation over a distance so enormous we don't feel it in our bodies. A distance so large that if we began walking it when the first pyramids were being built, we would still be standing at the edge of our own neighborhood, compared to that scale. So yes, 70 kilometers per second sounds violent, but it's gentle when hinted at locally. It only becomes monstrous when the distances become monstrous, and that is exactly what the universe does. It takes something quiet and multiplies it by emptiness. Now we face the real problem. We can't stretch a tape measure to another galaxy. We can't send a drone. We can't go there and report back. So we measure with the only thing that reliably crosses cosmic distance, light. But even light is not safe from expansion. As space stretches, it stretches the light traveling through it. Its wavelength grows longer, its color shifts toward red. That effect is called redshift, and this is why redshift matters so much, because it turns the universe into a kind of cosmic speedometer. Astronomers split a galaxy's light into a spectrum, like spreading white light into a rainbow, and they look for familiar patterns, fingerprints from elements like hydrogen. If those fingerprints appear shifted toward the red, it means the light has been stretched during its journey, which means the space it crossed has expanded, which means, with enough calibration, redshift becomes a distance tool. But this creates a bigger problem, because if distance is inferred from a stretched signal, then every distance we claim is already haunted by time. When we look far away, we don't see now, we see then. This isn't philosophy, it's physics. Light has a travel time, so the farther we look, the older the image. And in an expanding universe, there's a cruel twist. While that light was traveling, the universe kept expanding, so the galaxy was closer when it emitted the light, and farther now. It's like receiving a letter that took years to arrive, and discovering the sender moved away while the envelope was still in the mail. This is why distance becomes ambiguous in cosmology. There's the distance when the light was emitted, there's the distance the light actually traveled, and there's the distance right now, after billions of years of expansion. All of them can be correct, depending on what question we're asking. And that's not a bug. That's the nature of reality when space itself is alive. Scientists hate mysteries like this, because the universe doesn't just expand, it expands at a rate we try to measure, precisely. And right now, the measurements don't perfectly agree. One set of methods, using the early universe, points to an expansion rate around 67 to 68 kilometers per second per megaparsec. Another set, using nearer galaxies and stars, often lands closer to 73. That disagreement is known as the Hubble tension, and it matters because it's not a small aesthetic error. It suggests either something in our measurements is missing, or something in our understanding of the universe is incomplete. And then it got stranger, because data from NASA's James Webb Space Telescope has supported the same tension that Hubble Space Telescope data found, tightening the mystery instead of dissolving it. So we're left with a calm, serious possibility. The universe may still be holding back a rule we don't yet see. And now, place yourself inside it. You are sitting in a room that feels stable. The walls don't move, the floor doesn't stretch, your heartbeat measures seconds like they're solid objects. But outside this room, outside the entire Earth, The universe is quietly increasing the distance between islands of galaxies, not fast enough for our eyes, not loud enough for our ears, but real enough that it changes the meaning of every number we use to describe the cosmos. This is why expansion feels like a cosmic secret, because it's happening everywhere, and almost nowhere we can feel. So what have we uncovered? Space expands. The farther a galaxy is, the faster its recession appears, because more space lies between us to stretch. Redshift is the universe's signature of that expansion, light stretched into longer wavelengths during its journey, and distance becomes a moving target because the universe keeps changing while the message travels. But that's not the whole story, because expansion doesn't just stretch light, it stretches every possible conversation between distant places, every signal, every reply, every hope of quick contact. And this creates a deeper mystery. If expansion can pull regions of the universe away from us so fast that even light struggles to keep up, if distance itself is growing while information travels, then what does that mean for signals, for messages, for any attempt by anyone, anywhere to be heard across the dark? Because once distance becomes a moving target, silence stops feeling mysterious. It starts feeling inevitable. And that's where we go next. We live inside a universe that looks crowded, a night sky thick with stars, a galaxy so wide it holds hundreds of billions of suns, a cosmos where light is everywhere, and yet, when we listen for a voice beyond Earth, we hear almost nothing, no steady chorus, no obvious signal, no undeniable reply. That silence feels personal. It feels like the universe is refusing to answer. But this is where everything changes, because the quiet isn't proof of emptiness, it's proof of distance. Distance doesn't just separate places, it separates moments, it fractures contact, it turns communication into a slow-motion tragedy. And the disturbing truth is this: even if the universe were full of life, distance alone could still make it feel silent. Before we reach for cosmic explanations, we should start with something we already know. We have spacecraft out there right now. Real machines, real signals, real data. NASA talks to Mars with radio, and even at Mars' closest approach, messages take about 4 minutes to arrive. At the far side of the orbit, the delay can stretch to around 24 minutes, one way. Not because NASA is slow, not because the antennas are weak, but because the universe enforces a speed limit, the speed of light. And when we push farther, Voyager 1 is now so distant, over 24 billion kilometers, about 15 billion miles, that a one-way radio signal can take roughly 22.5 hours to reach it. That's still our neighborhood. That's still inside the sun's domain. So, when we ask, why does the universe feel quiet? We're really asking something sharper. How can anything feel close, when even nearby doesn't respond in real time? Imagine you're standing in a foggy field at night. A friend is somewhere out there with a flashlight. You shout their name, but your voice doesn't travel instantly. It weakens, it spreads, it gets swallowed by wind and distance. Now, replace the fog with space. Replace your voice with radio. Replace the field with a galaxy. And realize what we're doing when we search the sky. We're trying to hear a whisper that may have started traveling before our entire civilization even existed. The first reason the universe feels quiet is brutally simple. Conversation requires timing. Light-speed communication sounds fast, until we scale it up. Across Earth, light is effectively instant. Across continents, it's still less than a heartbeat. So our instincts get trained on a lie. Our brains expect the universe to behave like a room. But space is not a room. Space is an ocean where every message is delayed by physics. A message to Mars is minutes. A message to Voyager is nearly a day. Now push beyond the sun's reach. The nearest stars are not near in any human sense. A message across interstellar space takes years, not minutes. And that means any two-way conversation between worlds, if it exists at all, becomes something else entirely. Not a dialogue, a slow exchange between eras, a call that might be answered by the grandchildren of the person who sent it, and that creates a new problem. Because even if someone transmits, the reply is not just late, it might arrive in a different world, different leaders, different languages, different technology, different priorities. Distance doesn't just delay contact, it destabilizes it. But time isn't the only wall. There's another rule that makes the universe feel silent, even when signals exist. Signals don't stay strong, they spread, they dilute into the dark. Physicists describe this with the inverse square law. As a signal travels outward, it spreads across a growing sphere, and the intensity drops fast, catastrophically fast. Twice as far means 4 times weaker. 10 times as far means 100 times weaker. And once we leave the scale of planets, this becomes horrifying. A signal isn't a spear, it's a ripple, and ripples fade. So even if a civilization transmits by accident, through leakage, broadcasting, normal technology, those emissions don't remain bright beacons forever. They thin out until they become indistinguishable from the background hum of the universe. This is the part that shatters intuition, because in our daily life we can still hear something far away, a siren, a shout, thunder, but space is not air. There is no medium carrying sound, only light, only radio, only photons racing outward, and spreading into an ever-growing volume. People picture space as silent, but the universe is not silent, it's noisy, not with voices, with physics. Even when we point a radio telescope into empty sky, we don't get nothing, we get a faint glow, ancient radiation that fills the cosmos. The cosmic microwave background has a temperature of about 2.725 Kelvin. That number sounds abstract, so translate it into feeling. It means the universe itself has a cold, persistent afterglow, a leftover heat from the early cosmos, still humming everywhere, in every direction. And layered over that are natural radio sources, our Sun, Jupiter, the Milky Way itself. So when we try to detect a message, we're not listening in a quiet room. We're listening in a storm made of static from stars, galaxies, and the birth echo of the universe. Which means the question isn't just, is anyone transmitting? It becomes, can any signal stay strong enough, clean enough, long enough to rise above the cosmic noise? Now we reach the part that feels almost cruel, because even if we assume nothing about anyone else, no speculation, no claims, no fantasies, we can still measure one sobering fact. We have only been a radio-bright civilization for a very short time, roughly a century-scale moment. So our outward leakage, our accidental broadcasts, have only travelled about a century in light years. That means if our radio presence forms a sphere, its radius is only about 100 light years. Now compare that to our galaxy. NASA describes the Milky Way as roughly 100,000 light years across. So our entire radio footprint in the galaxy is not a flood. It's not even a wave. It's more like a single match struck in a cathedral. Most of the Milky Way would still have no idea we exist, simply because the news hasn't arrived yet. And if someone very far away transmitted something powerful, we might also be living inside their silence, not because they never spoke, because their light hasn't reached us. There's one more twist. Even if signals exist, and even if they're strong, we still might not detect them, because signals are often directional. A focused transmission is like a narrow flashlight beam. It can travel farther, cleaner, more intensely than a broadcast that spills in all directions. But a narrow beam has a price. You have to be in its path. So a civilization could be transmitting deliberately, aimed at a specific target without lighting up the rest of space at all. And we could be standing in the darkness between beams, not overlooked, just not intersected. This is why the universe can feel quiet even under generous assumptions. Not because intelligence is impossible, not because the cosmos is hostile, but because geometry is unforgiving. So the quiet begins to look less like a mystery and more like an outcome. Distance creates silence through three forces. First, delay. Messages take years, centuries or longer, turning conversation into archaeology. Second, dilution. Signals spread and fade, collapsing into weakness as they cross interstellar scales. Third, noise. The universe itself glows and crackles with background radiation, and weak signals drown inside it. And suddenly, the silence doesn't mean nothing is there. It means the distances are so monstrous that even something can disappear, not by being destroyed, by being stretched thin across the dark. And here's the unsettling part we don't like to admit. We're built for closeness. We're built for faces across a room, voices across a street, a horizon we can walk to. But the universe doesn't care what we're built for. Out there, even light, the fastest thing we know, moves like a slow messenger across a continent-sized history. So if you ever feel the weight of that silence, if the night sky feels like it's watching back without speaking, you're not imagining it. You're feeling the real scale of distance pressing against a human mind. And yet, that silence is not just a limitation, it's also a design. Distance is the reason stars can burn independently without merging into one blinding mass. Distance is the reason galaxies can exist as islands instead of a single crowded glare. Distance is not a side detail. Distance is the structure. So the question changes one last time. If distance can silence a universe, what else does it create? Because in the end, the most important thing in the cosmos might not be the objects at all. It might be the space between them, and that is where our story goes next. We began this journey the way humans always begin. We looked up, and we counted the lights. We thought the universe was defined by objects, by the things that shine, by the things that move, by the things we can name. But as we kept stepping outward, something happened to our sense of reality. The objects stopped being the story, and the space between them became the main character. Because distance isn't just a measurement. Distance is a force. Distance is a law. Distance is the quiet architecture that decides what the universe is allowed to become. And if we miss that, we miss everything. Scientists measure stars, planets, galaxies, and we tend to think those are the parts. But the universe isn't assembled like a machine. It's arranged like an ecosystem, where the emptiness is not wasted space. It's what makes stability possible. Distance is what prevents the sky from collapsing into a single blazing wound. Distance is what lets one star live without being consumed by the gravity of another. Distance is what lets galaxies exist as islands instead of one continuous crowded firestorm. So when we ask what the universe is, the honest answer is uncomfortable. The universe is mostly the space between things, and that space is not meaningless. It's the point. Let's take the most familiar cosmic object, a star. A star looks like a dot, but a star is not delicate. A star is a furnace held together by gravity, balanced on a knife edge between collapse and outward pressure. Now imagine what would happen if stars were packed close together. Gravity would tangle them, orbits would become violent, systems would destabilize, some stars would be stolen, some would be thrown out, some would spiral inward, and the night sky would not feel calm. It would feel catastrophic. But our galaxy doesn't work that way. Even inside the Milky Way, stars are separated by distances so large that our minds refuse to hold them. The nearest star system to the Sun, Proxima Centauri, is about 4.2 light-years away. That's not a poetic number, that's a brutal number. It means if a beam of light left that star system, it would take more than 4 years to reach us. In kilometers, that's about 40 trillion kilometers. In miles, about 25 trillion miles. Those numbers are so monstrous that they stop being numbers. They become a statement. We are alone on our scale, even inside a crowded galaxy. And that separation is not a flaw. It's what lets our sun exist as our sun. It's what lets the Earth keep a stable orbit for billions of years. Distance is why a star can shine without immediately becoming part of something bigger. Picture this. We're standing in a desert at night. Far away, someone lights a campfire, then another, then another. Each flame is bright, but only in its own circle. The darkness between them is immense, and because the fires are separated, each one can keep burning without stealing oxygen from the others, without merging into a single blaze, without becoming one destructive inferno. Now replace those campfires with stars, replace the desert with the Milky Way, and realize what we're seeing in the night sky, not a blanket of light, a scattered field of isolated fires separated by a darkness that keeps them alive. That darkness is not emptiness, it's structure. Now widen the frame. Stars are not just separated from stars, galaxies are separated from galaxies. And this matters more than we want to admit, because if the universe were dense, if matter were packed close, gravity would stitch everything together into a single continuous mass. No islands, no separation, no Milky Way, no Andromeda, no distant spirals and ellipticals hanging in the dark like lanterns. Instead, we would live inside something like a cosmic city that never ends, one continuous gravitational traffic jam. But that is not what we see. We see structure. Galaxies exist as distinct shapes because there is enough space between them for gravity to sculpt them over time without immediately collapsing everything into one place. Scientists describe galaxies as bound systems, held together by gravity, shaped by their matter and their histories. But their very existence depends on something quieter. They have room for stars to orbit without constant disruption, room for gas clouds to form and collapse, room for spiral arms to persist as patterns rather than chaos. Even collisions between galaxies, when they happen, are not like cars crashing. They are slow, graceful, terrifying mergers that unfold across hundreds of millions of years. And even then, most stars never touch, because galaxies are mostly empty space. So the universe isn't full of galaxies. It's mostly the separation that allows galaxies to be galaxies at all. This is where the story becomes philosophical, and still entirely physical, because distance changes what every object means. A star is not just a bright thing. A star is a bright thing that is far enough away from other stars to have an identity. A galaxy is not just a collection. A galaxy is a collection that is separated enough to become a coherent system. Even we, on Earth, are what we are, partly because our planet is not pressed up against another planet. We orbit in a region with space to breathe, space to be stable, space to persist. Distance is not an inconvenience we must overcome. Distance is the condition that allows the universe to have distinct entities at all. This is why it matters, because it flips our perspective. We don't live in a universe defined by objects. We live in a universe defined by separations, with objects embedded inside. Now we come back home, not to Earth, to something smaller, to something we almost never think about, to the distance inside ourselves, because when we talk about light years, our mind gets lost. So we need a ruler we can actually feel. Put your hand in front of your face, move it closer. Now move it away. That tiny movement is distance you can control, distance you can understand. And now the unsettling truth. Most of our thoughts never travel farther than centimeters. A thought forms, a signal moves through our brain, a decision is made. That journey is measured in centimeters, maybe less. Even our voices, our strongest human tool, fade quickly, a few meters, a few rooms, and then we look up and we see starlight that has crossed light years. We see photons that left their source long before we began our day, long before we were born, sometimes long before our species existed in its current form. And the contrast is almost unbearable because it forces us to admit something we don't want to feel. We are intimate creatures living inside a universe built on staggering distance, and you can feel that contrast right now. You can feel your heartbeat, you can feel your breath, you can feel the warmth of your skin. All of it happens in a tiny pocket of space, so small it feels like the whole world. But above you, every star you see is separated by light years. That means the night sky is not a ceiling, it's a depth, and you are standing at the edge of it, with a mind that evolved to survive a few kilometers of horizon. This is why awe feels like a physical weight, because we are not just learning facts, we are meeting a scale that violates our instincts. So what do we do with this? We don't treat distance as despair. We treat distance as the universe's calm decision. Distance is why stars shine independently instead of merging into one catastrophe. Distance is why galaxies exist as islands of light instead of a single, endless blaze. Distance is why the universe can have diversity, structure, history, identity. Distance is why anything can be itself, and that redefines the quiet. The universe is not silent because it is empty. It is quiet because it is vast. It is quiet because space is the dominant ingredient, not hostility, not rejection, not a cosmic judgment, just scale. And here is the quiet truth we can carry with us. We came looking for objects, but what we found was distance. And distance isn't the obstacle to understanding the universe. Distance is what the universe is.